Hello and welcome to section 5.6. We're splitting this section into two parts because there really are kind of two separate parts to it. And in this first part, we're going to be looking at the substitution method again, but this time for definite integrals. So we already looked at substitution or the substitution method for indefinite integrals in the last section. But now we're going to tweak that to adjust to definite integrals. Okay, so when doing a substitution with a definite integral, the new or different thing that we need to address is the fact that we have limits of integration here. So the limits of integration are the new thing on a definite integral. Indefinite integrals don't have these. So to handle these, there are two main techniques to choose from, and we'll look at them both. But you can either, number one, convert your limits to values of your new variable u, okay? Or number two, the other way to handle these are to keep the limits in terms of the original variable. So we'll just say keep the limits as x values for right now, because usually it's x that we're working with. But whatever your original variable was, keep the limits in those terms. But if you're going to do that, you need to use some sort of placeholder or just leave the limits off, something along these lines, until your expression is back in terms of that original variable. So let's see, until the integral is back in terms of x. Okay, because we're going to switch everything over to u. That's the idea of a substitution. So we're not going to be able to have limits as x values while we're working with the variable u. So you can convert your limits to values of u or keep the limits as x values but use placeholders. All right. So in this first example, we're actually going to go through this same problem twice using the two different methods here of approaching our limits. So here's our definite integral that we're going to look at. It's the integral from pi over 6 to pi over 3 of the function cosine x over sine cubed x dx. Okay. So first things first, we definitely need a u sub on this. There's not really another way to handle this integral. So we need to choose a u. All right, now think back to our methods from the last section and try to think about what a good choice for u would be here. Okay. So it's either going to be your cosine or your sine value here. So if we were to make cosine be our u, that would not be so good because the derivative of cosine is negative sine. We have sine cubed and it's in the denominator, not so good. So if you let u equal sine x, then the derivative of that is going to be cosine x, which is sitting directly in our integrand here. So the best choice here is going to be to let u equal sine x. Okay, because then remember, we need to convert this integral over into terms of u, take the derivative du dx, cosine x, so that we can work with the differential. Du equals cosine x dx. And how convenient that is, literally sitting right here inside our integrand. So that is awesome and a good sign that we're on the right track. Okay, So that is going to take care of the stuff inside the integral. If this was an indefinite integral, we'd be like good to go at this point. But we have this little issue of limits of integration here. Our lower limit is, I'll call this x1, is pi over 6. That's our first x value. And then x2, the upper limit of integration here is pi over 3. Okay, so for this first time through this example, we're going to use method number 1 here, convert the limits to values of u instead. Because when the rest of this integral is in terms of u, we don't want to have these x limits hanging on there. That's no good. So we need to convert. Switching the limits to u values. Okay, so this is an important step here. All right, so I'm going to start with that upper limit of integration. X2 equals pi over 3. And what we're going to do there is we're going to make an upper limit of integration in terms of this new variable u. We'll call that u2. And there is a nice convenient equation for this. It's our u substitution equation. U is the sign of x, and here we're saying x is pi over 3. So u2 is going to be the sign of x2, pi over 3. All right. And the sign of pi over 3, brush off your trig, is root 3 over 2. Okay. Now you're going to do the same thing with your lower limit of integration. x1 is pi over 6. And so u1 is going to be the sign of pi over 6. We're just plugging in our new x value there. And the sign of pi over 6 is 1/2. All right. So in doing this, now we're going to be able to convert this entire integral, limits and all. Everything is going to be in terms of u. So we are now going to have the integral from the lower limit of integration, u1 is 1/2, to the upper limit of integration, which is root 3 over 2. Okay, so we're putting in our u limits of integration here. And then we need to convert the rest of the integral as well, of course. So remember here, cosine x dx, that's going to be our du there. And then down here, we have u getting cubed. All right. So we're going to have du over u cubed. Okay, or to write that in a slightly friendlier format, 1/2 to root 3 over 2, we could say this is u to the negative 3 power du. Okay. And now everything here is all in terms of the same variable. So this is really nice. We're going to be able to find our antiderivative and plug in our limits of integration and evaluate this. So let's do it. The antiderivative of u to the negative 3 is going to be u to the negative 2 power and a negative 1/2 out front. Remember those evaluation bars? It's been a little while, perhaps. Okay. We're showing here that we're going to evaluate at our limits of integration. And I'm actually going to rewrite that here real quick as negative 1 over 2u squared. Just because I think it's a little nicer to plug things into that without the negative exponent. Okay. And so, yeah, we're going to evaluate now. First, plug in your upper limit of integration. So negative 1 over 2 times root 3 over 2 squared. And then subtract and plug in your lower limit of integration, 2 times 1/2 squared. Okay, and from here out, the rest is algebra. 2 times 3/4 there, plus 1/2 times 1/4. All right, good times in algebra land. Okay, looks like I am gonna get -2/3 plus 2/1. Okay. And so, yeah, we'll need to get a common denominator there. And we'll end up with 4/3 for our final answer. Because remember, definite integrals like this, they turn out to give you a value instead of a function for the answer. Indefinite integrals are the ones that give you a function. Okay, so there is our integral. It turns out to be 4/3 using this U substitution. And the key thing on this is that we were switching our limits to U values. Okay. Because right now we will do the same example, but we'll use our other approach here. We're going to do the same exact problem here, but this time we're going to keep the limits as x values and use placeholders until the integral is back in terms of x. Okay. So there's switching our limits to u values, and here is the exact same problem. All right. So the advantage of doing the exact same problem is that we already know what our u substitution is going to be. We know that letting u equal sine x is going to work out fine here. Okay. And so I'll just literally write the same stuff here. There's our differential du equals cosine x dx. Okay. Now here we are going to keep the limits as they are. We are not going to convert those. Okay, keep limits as values of x. And so we are going to need to use placeholders. Okay, while we are working with this new variable u. Okay, this is very important here. You can really get yourself in a world of trouble if you try and keep your x limits on an integral that's all in terms of u. Not so good. Okay, so we are going to convert this, but we're just going to convert the inside. Okay, so we'll have that du over u cubed set up again. It's the exact same integrand inside there. And now for the limits, instead of really writing anything at all, we'll just say like u1 to u2 without actually finding those u values. You could also say like x1 and x2 if you just want to keep it clear for yourself there. But yeah, you want to just put some sort of placeholder. Do not write pi over 6 and pi over 3 here. That is not good notation because these are x values, x1, x2. You do not want to write your x values on an integral that is in terms of the variable u. Okay, it's too tempting to try and plug in those x values, and it does not go together. It's not the same variable. So don't do it. Okay. So you're going to have here the same antiderivative process. All right, we'll still get our -1/2 u to the -2 power for the antiderivative, u1, u2. Okay, but here at this stage, we are going to go back to the variable x. Okay, So back to x. Okay. And so this is going to equal, now we're going to put our u substitution back in. Okay, so u is sine x. We're going to put sine x right here to the -2 power. There we go, right in place of where u was. And now that things are back in terms of x, we've done our antiderivative, we put sine x back in there. Now you can put those x limits back on here. So we can say now pi over 6 and pi over 3, because now all the variables match again. X, X, X. There we go. So the overall idea is you just don't want to mix your variables, because that can really lead to some sticky and confusing situations. Okay. So we'll put what we've got here. I'm going to, again, get rid of the negative exponents by slipping that sine x squared down into the denominator. And then you're going to plug in your limits of integration so that we can evaluate this. And so we're going to put in our upper limit of integration, pi over 3, subtract and plug in our lower limit of integration, pi over 6. Notice how I'm being very careful with my parentheses there, because we don't want to say like sine pi over 3 squared, because that looks like pi over 3 is getting squared, and that's not what we want to do. We want the sine of pi over 3 to get squared. So mind your parentheses here, they do matter. And note that you're still going to have to know your trig functions and your trig function values. We don't get to escape that. You still have to know that the sine of pi over 3 is root 3 over 2. You just get to do it a little later on in the problem in this case. So it's a lot of the same calculations that do end up happening. It's just when you decide to do them that changes. Okay, so as you can see, we are ending up in the same place as our previous method. We're going to end up with that negative, let's see, what was that? Just confused myself for a second there. Okay. All right, so we do end up with our -2/3 plus 2. And so we are going to get 4/3 again. I mean, it should be the exact same value. That's good, because it's the exact same integral that we were taking. So check. Same. Okay, so that is a good thing. So yeah, those are your two different methods of dealing with limits of integration. So you can do as we did in the second example here, keep your limits as values of x, and then just use some placeholders in the meantime while your integral is in terms of u. There we go. Once you go back to x, you stick those limits back in. Or you can convert your limits to u values at the beginning, and then you have an integral where everything is in terms of u, and then you can just plug in those u values because the variable matches there. Okay, so there's going to be some more examples to look at here, and you can try both methods, see which one you like better. Honestly, it's really good to know both methods, because the more tools you have in your toolbox, the better. Sometimes one method will be advantageous over the other one, depending on your problem that you're looking at, depending on the difficulty of converting your limits. A number of factors come into this. So it's good to know both, but see which one you like better. Try it out on the next couple examples.